Hello. So I'm Martin, and I'll talk about Sensor Snap. And basically, we're integrating wireless sensor nodes inside the snap fasteners for textile interfaces. And this work was mostly done at Google with Alex Oval, and also with the help with Thomas Vega from MIT Media Lab. So first, I'll show a little video of the Sensor Snap. So they're low-power wireless sensor nodes that seamlessly integrate into cups of a fabric snap fasteners. Sensor snaps provide a new technique to quickly, intuitively augment any location on the clothing with sensing capabilities. Sensor snaps securely attach and detach from ubiquitous commercial snap fasteners and user inertial measurement units. Sensor snaps can detect tap gestures as well as track body movements. Okay, so first, I want to start off with a high-level motivation for this work. So most of our interactions are done through a touchscreen of a mobile phone, and this is not ideal in many situations. So a lot of researchers has been looking into alternative wearable seamless interfaces, and especially the advances in electronics, miniaturization, and low-power integration. For example, like the chip on the golf ball is the smallest ARM microprocessor. This allows us to create new and explore new interfaces, and that's what we are doing in this work. We are integrating electronics into small sensor nodes. So specifically, we are looking into snap fasteners, which are commonly used in clothing and accessories, such as on like the jean jacket, the winter coats, as well as handbags, and many other applications. And they are very ubiquitous. So you can actually buy a kit of them on Amazon for like $10, which includes like a box as well as all the tools you need. And you can get them in like metal, plastic, different materials, and you can actually attach them at home. And the same way they can be attached in a factory as well. So this is a very like scalable fastener, very scalable invention. So they have 4 different parts: the cup and the socket. They sandwich a piece of fabric together. Usually they are pressed. They're like using a crimp tool. They're attached, and on the other side, you have post and a stud, which also sandwich another piece of fabric. And the socket and the post, they snap together so to secure the 2 pieces of fabric with an interference fit. And in our case, we only modify the cap of the snap fastener, and this is the part that faces the outside. And the other parts remain commercial off-the-shelf products. So we create the sensor snaps, the miniature sensor nodes that into the cup of the snap fastener, and they contain like a wireless communication, microcontroller, as well as sensing capabilities, and they are untethered with a battery as well. So our design requirements is we want them to integrate with the existing clothing and fasteners, and to be like ready to wear, ready to use. They should be easy to attach and detach to allow fast prototyping without use of complex machinery. And they should work with on unmodified garments. They also should be low power, so the battery can last for at least a day or more. They should be small and lightweight, so they're unobtrusive and to wear, and also they don't stand out during normal wear, everyday wear. So let's look at some previous work first. One of the common ways to attach electronics to fabric is using conductive thread and embroidery or hand sewing, like islands of electronics together. And this was done in Arduino LilyPad, which is a very popular kit for making conductive fabrics. The disadvantage of this technique that you need to modify the fabric. So it doesn't seamlessly integrate into the fabric. Also, it requires some skill to edit, and it always stands out because it's not part of the fabric itself. There is other approaches such as knitting and weaving, usually like using industrial machines that can be programmed like in the previous talk. So one of the ways to add the conductive fiber and conductive fabric, make this. One of the good examples is Google Jacquard, which added capacitive touch pattern on the sleeve of a Levi's jacket, and the snap fasteners were actually used as a connectors in this case. But the one difference from our work, this requires modifying the garment itself on a very industrial machines, which usually people don't have access to unless it's on a factory scale. The other approach is using straps and Velcro, and this is a very standard approach. So you can just strap devices. So it kind of stands out. It's not very seamless, but it's a very quick way to prototype. And we haven't seen any electronics being integrated directly into the fasteners or the buttons. We've seen the snap fasteners, the metal ones, used as conductors, connectors, for example, as an antenna in this case. So kind of looking at the previous work, usually the previous work required modifying the garments themselves to add electronic and sensing capabilities. In our case, our device works with unmodified garments, so this is one of the key differences. So I'll talk a little bit about the electronics. So we have an RF52 microcontroller, which has Bluetooth and ARM core. We also have a 20-pin port, which gives us access to all the pins, so we can add more like shields. We can also use it for charging and debugging. And you can see on the bottom that's a breakout board. On the other side of the board, we have an IMU, 9-axis gyro accelerometer, magnetometer. It's very powerful IMU. And the whole board is just 12 millimeters in diameter. It's 4-layer PCB. On the mechanical side, we created the enclosure using SLA 3D printing. And we have a 12 milliampere hour battery, which is probably the smallest battery that we could find on the market, which still allows for the Bluetooth capabilities as well as higher power usage. And the weight of our device is only 2.4 grams. In comparison to the metal fasteners, they're about 1 gram, so it's pretty similar in terms of weight. So the way we came up, we designed the mechanism to attach them to the fabric with the commercial snap fasteners, and we embed a hex nut inside the sensor snap, so that we can screw it directly with just using a screw we can attach it. Usually the commercial snap fasteners employ crimp tool, but we didn't use it because it applies a lot of force to the fastener, but we have electronics and 3D printed enclosure just cracks. And this is one example of attaching this. So you can see here, first we open up a hole with the cap of the plastic cup, then we put a screw into the socket, and then we push the screw to the other side of the fabric. Here's just using, and then we just put we screw on the sensor snap after that. And this is pretty much all you need to do to attach it, and this takes about 70 seconds. The commercial one takes 60 seconds. And the other side you would do as you would do normally with the commercial one using a crimp tool, which just crimps a little piece of plastic to make a permanent connection. And then you can see you can make it's a robust connection that you can You can open and close without as like just a normal commercial snap fastener. And so with the capabilities, we have gestures. So the main gestures are done with the IMU, so it's the tapping and rotation gestures. So the rotation gives us granular absolute angle, and then tapping is just like kind of like a button interface. And we can also create like a network with multiple sensor snaps. We can have a mesh network. For example, this is a tapping multiple snaps. So we can add more sophisticated capabilities. So the rotation gesture, we look into y-axis of the gyroscope, and this is our like raw signal over time from the y-axis. Basically, when we rotate the sensor snap left and right, we get the signal, and then we integrate it. We get a very pretty accurate angle. So this is from on y-axis, it's 30 to minus 30 degrees. So I'm rotating it left minus 30, then right minus 30, and then over multiple times. And we actually don't experience any gyroscope drift in this case. So the accelerometer gestures, the tapping is done with a z-axis. We only look at the z-axis of the accelerometer because the accelerometer would be too sensitive if we use other axes for false positives. So this is the raw signal with one of the taps. You can see there is a dip there. So we take the derivative of the raw signal, so it's done on board in real time. And then we set the threshold which corresponds to the taps. And once again, here is the gestures being performed, the rotation and the tapping. We also have a capacitive touch sensing. And this, you can see on the picture, we added electrode under the lid. And the capacitive touch allows us to have more granular control of the touch gestures. For example, we can distinguish short and long presses, but mainly we're using it as like a low power like wake up of the device, because the tapping with the IMU is very sensitive to motion, and this is not sensitive, so you don't have a lot of false positives here. Only when you touch it, it will trigger. So that goes into our interaction modes. So in a standby mode, we only look at the capacitive touch. So this is the capacitive touch is periodically censored, and then the processor goes to sleep. Then sensor goes to sleep, so it's duty cycle, very low power. If detects the touch, it goes into the gesture mode where it again sends the gyroscope and accelerometer. It turns on the IMU, and the Bluetooth is its sampling rate is about 20 hertz, so we get real-time data. And this is the gesture that I showed. And then we have the motion mode where the rotation matrix is extracted from the IMU, and this is a very power intensive. So we get about 4 to 15 hours in a standby mode, depending on how often the capacitive touch sensor is sampled, and we get about 40 minutes in the gesture mode. And here is some of the examples. So we have a music player where we connect the sensor snap to an Android phone, and we made an app for like a music app. So you can have here we can so we use a tapping gesture to start, pause. We can rotate to get to change the volume left and right. And also we do double tap, and then it goes into a different mode where we can rewind and fast forward. So you can see we can add this kind of capabilities anywhere on the body without much modification to the clothing itself, and this is ready to wear. As well, we also have a motion sensing So this is using the rotation matrices. So you can see there is a digital avatar of my arm, which kind of repeats the motions that I do. And this shows also the capability of meshing, like, so you can have multiple of those buttons working together to provide more functionality. So in the future, we want to improve the charging, so we want to use wireless charging so we can waterproof and make the enclosure more robust. We want to further miniaturize the size. So, for example, if you could make it like those buttons on a shirt, like very small, but it's pretty challenging. The ones with like 4 holes, it's still hard to do. We also want to optimize the power. Mainly, we could use a lower power IMU, which will save us a lot of energy, and we can create new software so the users can create custom interfaces more easily with like multiple buttons. Right now it's just we only have pre-programmed interactions, and we also want to look into other applications. Can this be, for example, this is used as an earring? Can we use it as jewelry, accessories? You know, kind of universal platform for like little sensor nodes on the body. So in conclusion, we made a wireless sensor node inside the snap fasteners. They are quick to attach and deattach, and they are compatible with commercial off-the-shelf products and don't require garment modification. So they can actually be employed both in mass manufacturing as well as in hobby settings. The current cost is like to manufacture was like about $10, but we think this could be much cheaper if it's done on a mass scale. And we show applications that utilize the IMU and capacitive sensing. Thank you, and we'll show a demo today at 6 p.m. if you want to see it.
Great, thank you for that excellent presentation. So many practical applications of this work. So we have time for one very quick question.
Hi, I was wondering if you could speculate on making this thing batteryless, or how you envision people having to change batteries over time.
I mean, there's definitely like RFID technology. You could make it batteryless, but it's also you know, the battery technology and like the power consumption is pretty good now, that we can actually have batteries on those things, because the battery allows us to have a lot we can have a lot more functionality with the battery. So I think the kind of the future of this kind of stuff is like with the batteries, not without them, because it's just a power problem right now. So the batteryless stuff is very limited, especially for interaction, for something that's wearable. You want to, like, you know, when you touch it, you want to have you want it to respond immediately, and with the batteryless, you don't usually have that, because it needs to harvest the energy. Then it's very periodically, you know, activated. So, but it's an interesting direction to look into as well, you know, for some areas, especially sensor.
Thank you. Let's thank Artem once more.